Oh. I need to run the game again. What's what? Oh, it is. Right. Should be back now, guys. Post back in there. Right. So, as usual, we mess with the GPU and it gives us a crash and crashes the stream. I don't know if this is an AMD driver thing. Maybe is. Oh well. That is life. So we did a thing and it blew up. So do we have an infinite loop? Did we have? All right, we didn't increment the word index. That is, it must be it. We read a word from the buffer, didn't bother take up anything, right? Then this one, oh, I've got to be super careful about this. This is so bad. Clip word. Oh, horrendous, right? Ooh. So, this will work. Pretty sure. So it's coming from the clip words. We're up in the index now correctly, which means we'll do a circle, then a finish, and then it will break out. All right, let's try that one out. So with NVIDIA, I recently used the memory address as an index and it just renders the void. Excellent. Complete opposite. See, on AMD, if you have a descriptor set, right, like it's really bad. Like you have an array of descriptors, right? You got your like, and you know, you've used descriptor indexing, which we do. So we use like bindless, right? So we go, oh, our buffer is in index 2, and we're going to use that buffer. And what happens if your buffer index is uninitialized and you go out the descriptor pool somewhere, or whatever you call it? Well, it crashes the GPU really bad. Like the whole window manager goes down. You just crash. That's really bad. Right, so hopefully we don't crash again. Let's give it a go. I think it should be fine. Oh yeah. So the problem is we didn't actually clip anything, which is a damn shame. I was hoping for a legendary clip. So is this just too big? Oh my days. Oh, we're so lucky. On the finish, you're meant to read the soft. Yeah, right. We've got to be careful about that one. You don't read the soft off. No, I'm not popping off. The A collection of stuff, welcome back. Yeah, we're not popping off. We just crashed the driver. So the stream shut down for a sec. It will drop the end of your index buffer if it isn't aligned. Crazy. Yeah, ARM does a lot of like optimizations under the hood in their drivers sometimes. They do some weird optimizations. From what I've heard some things. I'm not experienced with them myself. Am I thinking that this radius is just too big or something? Oh no, we didn't do anything with the clip. I set a variable called clip and I was like, oh yeah, that'll work. Right, clipped. If clipped, we continue. that simple. It's that simple, isn't it? Ta-da! Clipping. So obviously you get some rough edges, right? So you need to anti-alias those as well. Introduce more anti-aliasing. But you get the idea, right? We can put shapes down and we can do some clipping. Now, should we do the anti-aliasing and then we'll do a soft clip? And then after that, we're going to bring in all of these shapes and operations that we have down here. We're going to bring these in to, you know what? We could get rid of the clip words buffer and just call it, yeah. We could get rid of the clip words buffer and just use the draw words buffer for where the clip goes, but never reference it as a draw command. But it's a clip instead. And then that would eliminate these problems and make it able to share the code even easier, I think. Yeah, that would be good. Yeah, I like the idea of that. But I don't know how I'll share the code, to be honest, because we've got an array of clip. We could share the functions. It will get inlined anyway. This is the thing, it will get inlined. So repeating the code isn't probably an issue, other than the fact you've just got duplicate code in places. So maybe it's fine just to copy paste it, in all honesty. Yeah, screw it, let's just copy paste it. And the other thing as well is I want to check how bad it is to have all these switch statements everywhere, because I don't know. Seems like it could do a lot of allocate a lot of yeah, it could be quite bad. But we'll see. I don't know, should we see how good it is now? I think we can download the AMD SPIRV to ISA compiler. I think you can download it. Because we want to get because if we can convert our SPIRV code into the actual assembly, we can see how many registers it uses, and I want to see if this crazy clipping is just going to make it even worse. Well, no, it will make it worse. I just want to see how bad it is right now before we do this crazy clipping. So we should be able to get the compiler, and it will literally just give us assembly, right? Like this stuff. And we can just see the register allocation on it. Right, where's the bugger? Gotcha. Right. So in here there should be a shader compiler from SPIRV to AMD assembler or something. This is it, AMD LLPC. This one. So we should be able to run this guy on our shader. So we're going to grab our shader. Oh no, we won't. Right. Open terminal here. Okay. AMD LL. Right. Like I'm programming on Windows here. Right. Look at this bugger. So we've got to find a way to put our things in here. So we want to pass in the input file entry point. Right, I need to pass in the entry point as well. So we'll say, put in our spivvy file that we made with our compiler. We'll put in the entry point, and then it should give us. It should give us a dump of the. Like, I don't know if we want an output file, but we want to like view how many sort of like registers there are. VGPR limit, right? Show instructions, dis instru. Right. Yeah, talking about dump. Yeah, I want to see how many VGPRs we're using on the on an AMD GPU. Because if we, yeah, so there's a VGPR limit. We might have to set that to what my GPU is. Because when you have a lot of branching, you're going to create a lot of. Like we've got loads of branching here, and it gets big, right? You're going to create a lot of like register allocation, and when you fill that up, it's going to spill those registers into some memory like this, in a way, and that you get take a performance hit for that because it's got to read and load it from memory. Basically, it's a bit like putting it on a call stack. So we just want to make sure that the shader that we got, see how many registers it's really allocating and see what that's about. So if we pass in our, so we go to home workbench, home workbench, gamevet engine, build, and then there should be shaders.spv, right? Really nice thing. Now, I think it says you want to put a comma, and I think you got to find your entry point. So entry point is gfx underscore cs for compute shader underscore UI renderer. So gfx UI or cs UI renderer. Right. So it's saying has unknown extension. Don't do this to me. your GPU thing compiles this. Why are you? Oh, they mean file extension. Because they can't just read the first 4 bytes of the file and be like, oh, this is spivvy. But instead, they want to do a horrendous. Right, so we'll. Right. 2 seconds. ls ln. You know, I forget how to do this. Symbolic link. No, ln, sorry. Target, then link name. Good. Wait, is that right? Create a link to target with link name. Good. So we're going to say ln-s shaders. So that's the target, and the link name is shaders.spiv. Because apparently they can't just check those. Seriously, AMD, why do you do this to me? That's what they want, right? Damn it. First validate spivvy. You haven't got the scalar block alignment, my friends. Scalar block layout. They could have got that again from the binary if they just read it properly, but no. Actually, no. No, no, I don't think they could have actually. What? What? This was the ARM craziness. Imagine having to debug shader crash. Oh yeah, this is the one that I remember seeing. Yeah, this is it. Yeah, so yeah, so yes, first with non-existent indices can also be processed. Uh, ARM GPU shade vertices in groups of 4 contiguous indices. We can shade indices your index buffer skipped. Uh, right, yeah, yeah, yeah. So you can just say 0715 and it does all of those. And if it's not aligned as well, that's horrendous. Does this even like go with a spec? Tightly pack the ranges to minimize. The pad attribute, multiple votes of 4. Yeah, multiples of 4, and you can't skip them as well. Crazy. Isn't that the whole point of an index buffer, though? Um, but yeah, it's crazy. Did I miss an episode of you from the Rustless? I'm not sure what that is, or what you're referring to. Um, so why? Structures decorated with block push constant storage must follow standard storage buffer rules. Yeah, that's why you scale a block alignment. So you align to scalars. So where is this under? Is this under like valid an extra flag section somewhere? General options. The options go before, which I did. This is rocket science, yeah. Right, I don't know if we can get this to work then. Scalar block layout. I copied and pasted it. Like, and this is presumably their driver. Well, their driver uses anyway. Right, let's see if we can. Spivvy dis, Spivvy. Yeah, it's all Spivvy stuff. We see if we can run their What do we want to run? The GPU analyzer? Get ready to blow up my computer. Alright, it's executable. Why doesn't this work? Radeon. Vulkan. This theme is just doing it wonders. Compute pipeline. Huh? Right. Nope. Ain't doing that one. Yeah, that was horrible to even like look at. GPU analyzer. That we looked at. I don't know. Yeah, it's just a whitewash, you know? Pinnacle. It's horrendous. Oh, I want to get this to work, but I don't think it's going to work, guys. It's, being a silly. Like, I'm trying to just compile my shader as... Enso's pretty good. Yeah. But you can't get the assembly, right? But I can't get the assembly right now of an AMD card, but yeah. Do they offer that in... Do they offer like... Or yeah, they probably show how bad you're allocating the... Because that's what we're trying to find out, right? Is are we allocating too many registers in the shader? So I'm just trying to look at. Let's go into Google and type like AMD LLPC. See if anyone's got like some example that they use. Oh, it's just a single dash, is it? That would be amazing if that works. No. If I completely take it away. How's it going, very much? How you been? It still fails on the same one. Horrendous. Right, can you give me like a nice example? Dash GFX IP. What's this GFX IP? Excuse me. Right, no luck. Yeah, it's just horrendous. Like, you would think this is like... This is what they use in their like driver or something, but no. Oh, the standalone compiler. Oh yeah. Same docs. They can emit LLVM apparently. There's a dash V. Let's see if that works. Whoa. So just output on my... Oh, okay, just did disassembly on my... Yeah, I get that. It's valid, I swear. Right, let's run it through spear v val and see if it likes it. Spear v val dash dash scalar block alignment or layout. It's fine. You get rid of this and it complains. Damn these things. Right, so I guess we're not going to look into that now. I guess the only other way you can tell is you got two options, right? Removing code and keeping the same drawers around. So removing code that will never get executed but will be branches in the code base and it's just seeing how much better it will do. And then you can probably find a threshold where it gets really bad. And then that's the way we can figure out. Or maybe using some other tool they've got. But yeah. Right. Hmm. Can I not edit the spear V? Well, no, because then it messes up my alignment. And then the stuff gets all buggered up. Their compiler is probably open source, so you could probably find the problem there. But it just feels like effort. What are you searching for? Well, I was trying to use the AMD low level, I don't know what it's called. Pipeline compiler and compile it down to AMD's assembly so I can just see how many registers it's trying to allocate for my shader because I want to see if it's going to be a problem because I'm about to add a ton more switch statements basically. So I was like, okay, I'll just see how it is right now because I've already got a ton of switch statements and it's not working. Like they do the smart thing of trying to validate the SPIR-V file, but they're not passing the arguments incorrectly. So maybe I need to put it, maybe I need to put them afterwards. Should we try that? It sounds like the graphics equivalent of moving lines around in a GC language in an attempt to get lucky. Jitted. To yield less allocations. No, not really. Like, the idea is, like, you can't just move code around and make it better. You'll hit a limitation, and you just gotta have less branches. Or, like, just remove the complexity, basically, from your shader. So I'm thinking that maybe if I put it afterwards. Scalar block layout. So if I put some garbage in there, it says it's an unknown argument. So it does take it in. So I think I might be missing some other thing then. So we read through it again. With Regit. Oh, how indirect it is. Right. Yeah. I see what you're saying then. Yeah, it's a bit of a shame. Like basically they're just GPUs kind of suck. No, they're just really crap to program for. They do a really good job of making stuff go fast with just the programming model, but the programming model is really like, it's that black box type of programming. Yeah, so trying to move around at the high level. Really go around so to get better. Oh yeah, yeah. Sorry, I see what you're saying. Yeah. So you're saying like the fact I have to like delete switch statements just to see if, and then measure the performance just to see if it actually works. Yeah. Hmm. Yeah, I feel like that's what I might have to resort to. Um, like we could literally just try it right now and see how, like, it's not too hard. Um, so you have a bunch of general options, and it's just all in general, is it? It's just all in general. So you have a bunch of like enables, dump. See, the fun thing is they actually use like dwarf as well, for some reason. But they don't really give you access to that, I think, to actually like do any graphics debugger thing. It's weird. But yeah, the SPIRV stuff isn't really going to be SPIRV convert. No, no. Um. Oh, dash dash validate SPIRV. Well, guess what? You're doing it already. Default to true. This is how we get around it. Dash dash validate SPIRV false. Let's try that. Please work. Right, so it says default to true, but you've made it like a flag. Which makes me dash dash SPIRV workaround bad SPIRV. Enables workaround for bad SPIRV. Mine, I ain't got bad SPIRV, my friend. My SPIRV is legit. Is it really called workaround for bad SPIRV? SPIRV. Don't you dare do this to me. Right, I'll put it before like it wants it to do it. Validate. Can we say equal false? Things happened. Right. So now we've got to figure out how do we get a binary out of this? Oh, trust me, bro. That's just trust me, bro. With it, yeah. Oh, the triple shift left stuff. Yeah, not nice looking, is it? Have you tried some sort of underscore debug variables? Since some shaders need to go through Mesa on AMD GPU. Ooh. Oh, look at that. It's funny how it happens at any stage, or 3 layers deep, deeper than a Unity dev, but this kind of issue's the same. That's just bringing up here. Yeah, and no, software's like really bad. Like, we make stuff too complicated. Like, you know, there's probably like tons of people who work on all this stuff, and really it all could just be thrown away if we had a simpler approach. Like, you know. Programming. Right, I want to take a look at that link that was dropped. Oh my days, that scroll animation. That got me. Right, you're saying there's an underscore debug. There's environment variables? If set, error message print standard out. Oh. I realize these things exist. Print debug info. NIR. So that's their sort of like, so when you you get your spear V, it gets transpiled into NIR, which is, from what I understand, which is basically, it's their equivalent of an intermediate. Yeah, it's like their version of SpearV basically. It's like LLVM IR, and then I think they do optimizations on that, and then they lower that into the. And there's probably many stages of this. So there's debug, compensate relative to apply to shaders, help. Okay, the list of them. Fair play. Right, so you can probably get it to dump the stuff. I did not realize this existed. This could probably be quite easy to use if I just knew all the stuff. That's the issue with it. So the thing I want is probably rad v driver debug. Right. Enable the LLVM. Right. What I want is some form of dump of the sort of binary they have at the end, not the spear V. Dump shaders maybe. I want to view their VGPR stuff. Info. Yeah, let's say dump shaders. Let's see what that does. Should we try this out? So, how do you do these things again? I gotta remember how I. Right, so that runs. Good. So if I do like this equal. So we go to our game and we say this equal. Let's say shaders. Is that how you do it? See, I'm dumping a lot of crap into the terminal. Oh my days. Would you look at this? So this is AMD's shader code. Oh yeah. Now, do we get some V? So these V's are the VGPRs, right? These are vector, right? And these are vector registers. These V1s, and these S1s are scalar registers. So the scalar ones are shared across every thread that runs in lockstep, basically. So what I want to try and find is probably the function that we want, right? Right, so we dumped that into the... I did not realize this stuff existed. This is cool. Thank you. Build shaders dot, I don't know, text. It didn't work, did it? Right, this is my program. So, do they dump it in standard out? Like what are they logging it to? Because it goes to standard out. They put it into standard error then. How do you do it? It's and that, isn't it? I don't know. How do you pipe standard error? It's not standard error because it goes first, isn't it? So what other one would it be? So 2 and, right, and 1 T dash I. Thank you, sir. Appreciate it. So let's try that. Hopefully it's because of standard error, but I don't know if it would be. Now if we go... Right, we've got it all in here. We can see it. Legendary. So what we're looking for is... Right, so we're looking for that sort of like GFX CS. Well, obviously not, because we get to the profiling stuff. But what I was hoping to see the... So the biggest problem then is... Right, so there's a bunch of compute shaders. We've only... Oh! So maybe we can tell it by the workgroup size. Well, we've only got like... Right, let's have a look at how many computes we've got. 111,888. That's the clear. That's a small one, right? We've got another 888. That's the massive one. So we should be able to find that in there. So we're looking for this. So this is obviously the small one, right? Right? No? Maybe. Yeah, that's the small one. This is the big one. Yeah, this is it. See how branchy it is? Right, and I'm seeing a lot of... So I want to know... Like, okay, so first of all, this is a dump of something else. This is probably a dump of the... This is not the assembly. So we've got to keep going. Oh, is it? Shader stats. Bam. Oh, legendary. Let's try that one. This would be amazing. Right. So we look for the worst one, basically. So there's 3 shaders, they got that right. The code size, there we go. So these are the small ones. And this is the big one. Right, so we only got 40, so it did 128 SGPRs. That one, I don't know why it's 128, because these ones barely use anything. So I guess we just ignore that. This has got 40 VGPRs, which I think is fine. I think that's fine. Yeah, Twitch is better than documentation, exactly, yeah. The amount of stuff I learned, the information I get from the chat is just really, really decent. It helps me solve problems in better ways that I wouldn't even thought of, basically. So there's no scratch yet, so it's not spilling, right? So 40 VGPRs, I think that's decent, right? And we've already got quite a lot of branches. So the thing is, as soon as we so we might be doubling it, which is when it's a bit of a problem. So we want to see how many VGPRs we have per core. I forgot what it is. AMD RDNA 2. See, obviously I'm sort of targeting a very specific architecture here, but they have very similar ways of doing things in a way. Whereas how many VGPRs do you have per compute unit? It was saying that doc, isn't it? VGPR. Allocation alignment. Are allocating groups of 8 D words for wave 64, 16 D words. Wave 32. So I'm not sure which one we'll be doing, to be honest. That would be automatic, wouldn't it? But we've done 8 by 8, so I assume it would have done 60. What did it do in the end? Right, so we've got this pre-scheduled 10. Right, so it's telling us how many it's probably going to be using exactly. But it has to allocate them in groups of, interesting, of 8 or 16. So this might be... It does in 8, so this is in wave 64 mode. Right. Because that's round up to the nearest 8. because that's how much it actually used. Right, so that's good to know. So where's the VGPR count per compute unit? That's the next question. Well, it's not per compute unit, is it? It's over. There's a probably. See, this is where my knowledge gets a bit. I don't think it's per compute unit. Maybe it's not. Right. I'm just going back to the same docs, aren't I? So VGPR. Let's just search for that. Right. RDNA processor consists of a scalar ALU, so arithmetic logical unit or something like that, which operates on one value per wavefront. So a wavefront is like 64 threads or 32 threads running in lockstep. A vector ALU, which operates on one unique value per work item. So per work item means per thread on the per thread. Well, thread, right? It's not really a thread, but yeah, per thread, whatever. That runs in lockstep on the compute unit. So let's just quickly read this. RDNA kernels are programs executed on by the RDNA processors. Conceptually, the kernel, which is the compute shader, is executed independently on every work item. But in reality, RDNA processors are groups of 32 or 64 items into one wavefront, which executes the kernel on all 32 or 64 wavefronts in one pass. Right, so work item is like a thread, and wavefront is the group of 64 or 32 threads, okay? So you got this local data storage, which allows work items within a work group to communicate. So if you got these things running in lockstep, you have that local group size, right? We've done 8 by 8, which is 64. But if that was like 64 by 64, you got many wavefronts running. And for those to communicate, use the local storage. And you want to make sure that you then use a barrier and stuff like this. But that's not stuff we're using. So we'll skip that. Scalar memory, which can transfer data between SGPRs and memory through a cache. Vector memory that can transfer memory between VGPR and memory, including sampling texture maps. Right, I'm not sure if that answers our question. Yeah, we just want to figure out how many of these guys do we have. Is that an architecture thing or a per GPU thing? Right, so there's 256 addressable. But I don't think you want to fill it up because they might be shared between. There's something about it. I think, yeah, so we've got to. Yes, there's 256 addressable. So it's just a bunch of like instruction stuff saying it's invalid if it's out of range or whatever. Allocation and alignment. VGPRs are allocated within groups of 8 or 16 D words depending on the wave size, right? Operations using pairs of VGPRs, example double floats, have no alignment restrictions. Physically allocations of VGPRs can wrap the VGPR pool. Okay. Cool. Wave shared VGPRs. Wave 64 can allocate wave private and wave shared VGPRs. Private general purpose registers are the normal ones where each lane, so that's the thread, right? So, and that's the work item. They always use this mixed terminology, which is really confusing. Has a unique value, right? Whereas shared VGPRs are shared between the higher and low values of the wave 64. This can be useful to reduce overall VGPR usage when combined with subvector execution. Shared VGPRs are allowed in blocks of 16 D words. So I guess that is when you do the wave operations, maybe. Got to have a think about that. Shared VGPRs locally occupy the VGPR addresses immediately following the private VGPRs. Right. If a wave has 8 private VGPRs, the shared ones start at 8. Yep. Shared cannot be used for exports or GDS. Okay. So GDS is this thing that I don't think you really get access to. It's weird. Oh. Right, so anything that tells us the number of these things, and when you start getting, because I've heard of like, there's a thing called like register pressure, and wait, no register pressure. Well, anyway, if you, yeah, I need to figure this thing out. Compute shaders have up to 3. Right, so they initialize the first VGPRs to these guys. So, yep. So it just stores a single float, right? Each VGPR stores a single float, but there's one per thread, right? So some are shared across them all, whereas others, right? Wave temporary VGPRs are available. In Wave 64, each wave can be declared normal VGPRs. Register spilling. No, not quite spilling. So spilling we know. Spilling we know if we go above 256, because that's the most addressable, we'll get some spilling. And we're not getting spilling, which is great. And we're nowhere near it. But what I want to see is like, as we increase these VGPRs, is there another problem that we'll get? Oh, 256 for the entire seat. Is that right? I'm not sure what it is. It's like, I'm trying to remember. It's like something to do with like, yeah, this sounds like something I want to know. Given basically 64K, yeah, 64K available VGPR for the entire CU. So CU is 64 threads. It's got the VGPR memory, SVGPR memory. It's got the arithmetic units for both scalar and vector, right? Each thread may require, at maximum, 32 VGPRs at any time. Really? So why if it's got 64K, why can it only do 32 at one time? Because obviously, if you do 32 times 64, you're not getting. What is that number? Yeah, you're only getting that number, right? Whereas if you do 256 times wait, what am I doing? Yeah, 256 times 64. Did I type that in right? There you go, 16k. So something about that information feels wrong to me. Right, there's an optimization page. Okay, brilliant. This is a GCN. What about RDNA? So GCN is quite similar, but RDNA. Right. RDNA did some things. They made. What did they do again? AMD GPU architecture. There's a wiki page on it. There's a really good wiki page on it. So RDNA 1, the differences introduces what's something to do with the SIMD slots. Yeah, so rather than having so their ALU went to the size drop this to native 32 wide at the same time. Meaning the wavefront now matches the SIMD size. So I'm not sure why that's different. But yeah, SIMD I guess means the ALU. And then I guess wavefront means the number of the memory you have to store the independent data, right? So that's what they introduced in. So they upped the. So it means they don't have to run the same instruction twice on the different pieces of memory or registers, right? Issues, instructions. Right, let's go read that page. GCN includes 4 SIMDs. In this case, it'll be 2 SIMDs, right? Is that right? Each 60 register file. Every C register file of 32-bit. Yeah, we might have to see what that is for the. Try and look at this. Where's the compute unit? Architecture. Close this garbage. Just the instruction set architecture. It's not quite the architecture. Whoa. Legendary. Right. It might just be a set recommended maximum number of registers to use. Yeah, but if it's recommended for a reason, right? There's a. Well, apparently I got ray tracing. Not like I'm ever going to use that. I need me some VGPRs. There's a video. Gen Z, I'm in. Gen Z me is I'm in. Video. I can't see anything of useful information in here. Right, okay. This is really bad. Right, Wikipedia, source of truth. Right, nothing about VGPR. You bastards. Yeah, it contains 2 sets of SIMD32 units. Um, 2 sets, so you can run them. We get, but it's just the register file. Epic gamer information. Yeah. This things make your arrays go boof. Right, so when you find in there, that's just the instruction set architecture thing. Where can I get my informations? VGPR register file. What is this? This looks good. Right. Here we go. Right, let's turn off Dark Reader, because Dark Reader's like, we're gonna make it go dark. And it just inverts everything. So yeah, this is the picture I showed in that devlog for the first devlog, right, when I was introducing the thing. I was like, we're just gonna leverage the compute units, because guess what a GPU basically is? Compute units, right? You know, there's a little rasterizer thing here, right? There's some other little things, but for the most part, it's just compute units. So why don't we just use the compute units, right? That's the sort of thing behind this project, right? But anyway, we're looking for the number of VGPR and to get an idea, right? So this is a thing that we can look at. Oh, we found a thing. The superb performance and efficiency of modern graphics processors is derived from parallel computing capabilities of vector execution units. As Figure 8 illustrates, one of the biggest improvements in compute units is doubling the size of SIMDs and enabling back-to-back execution when using more efficient Wave32 wavefronts. The new SIMD boast instruction per clock, I think that means, and cuts latency by 4 times, not 4x like the Americans say. It's just by 4x. Anyway, so right, so you got your compute unit. Oh yeah, this is GCN, right? So yeah, 4x, where x is equal to 1 divided by 4. Yeah. Oh, days. I don't know why they say that. They just see the x and they're like, I have no idea where that came from. It's in every like conference talk. It's obviously American. It's really dumb. Right. Previously interweaved. Right. We're seeing numbers now. This is good. I see good numbers. Right. Previously interweaved vector approach in GCN required scheduling other instructions around 4 cycle vector instructions. So it would take 4 cycles to do a vector instruction. Maybe because it has to do it. It has to do it twice, or maybe 4 times. Yeah, but there's 16 wide, so it's running wave 32, just do it twice. I don't know how they dropped it to 1 cycle though. That's pretty impressive. doing it across all those threads. The larger the RDNA dual compute unit also specifies compiler design and enables more efficient code by scheduling and issuing independent instructions every cycle. To accommodate for narrower wavefronts, the register file has been recognized. Each vector general purpose register, VGPR, contains 32 lanes that are 32 bits wide, right? And a SIMD contains a total of 1024 VGPRs, 4 times the number of registers as in GCN. The registers typically hold a precision of 32-bit data, but also been designed efficiently for handling mixed precision for larger 64 data. Adjacent registers are combined to hold a full wavefront data. More importantly, the compute unit of vector registers natively support packed data, including half precision and 4 8-bit integers or 8 4-bit integers. Right. So let's digest this. There's also this down here that we can read. But let's digest what we just read. So it's saying that they've got these, which is 4 times the number of GCN, right? So we've got 1024. And what was the number you put down earlier? 32 VGP. So it's not right. Those numbers don't seem to correlate with what Acrez pulled out from that other thing earlier. So I guess what they had then was 256 VGPR in GCN. But now in RDNA, this is RDNA though. What did they change in RDNA to? Let's go and grab. Why is this information so difficult to get to? You got to go over there, compare RDNA architecture. There's the wiki article, right? Good old wiki. Why is this dark reader off? So I just need to turn it on for that. Okay, I guess. Right. So from RDNA, so differences from GCN. So they did the single clock cycle instruction issue. Did one instruction per every 4 cycles. RDNA does it 1 instruction per. Pretty incredible. Wave 32. GCN used 64 threads. That's why it was 4 instructions per cycle, because it's got SIMD16, right? So SIMD16 means it takes 4 cycles to do. So run the same instruction 4 times that it reads to get the 64 threads to work, right? And the reason why they used to do this was so they could spend the time that it took to do a texture fetch, from what I remember hearing. But now I guess they shifted to more compute shaders getting more complex, so they wanted to reduce that time now. But instead they were just most of the time spent waiting on texture fetches anyway, so that didn't matter from what I remember hearing. So RDNA 2, so RDNA, this is RDNA 1, supports both 32 and 64. Okay, that's all the current stuff anyway. GCN grouped the shader hardware into compute units, which has scalar ALUs, vector ALUs, LDS. One CU contains 4 SIMD16 units. RDNA introduced workgroup processor, replaces a compute unit as a basic unit. So that's got 2 CUs, which is 232 SIMD units. So it's 2 independent CUs basically, but they can run together in lockstep, giving you wave 32 or 64 mode, which is pretty sweet. This allows significantly more compute power and memory bandwidth to be directed at a single workgroup. Right. So that's given us I thought they would have specified something else in this change, but what else did I want to pick up on? What else did I want to pick up on in this? Do I want the dark mode on? I don't know, maybe. Who wants the dark mode on in the poll? Dark mode on PDF. Yes, no. 1 minute, go. Let's keep it on though, because it just keeps blinding our faces. So the thing that we read that made me want to go down that route was to accommodate for the narrow each. Take a bit of a sip. To accommodate for the narrower wavefronts. Narrower wavefronts. The each virtual register contains 32 lanes. That is 32 bits wide. And a SIMD contains a total of 1024 VGPRs. Right. So that's shared between. Right. Can you see this? So this is a workgroup processor. It can run 32, it can run the low 32 and the high 32 on different shaders if it wanted to, and it shares the VGPRs between. Right, so this wave 32 mode is where it becomes a problem. You get the half the VGPRs. That's it. So in wave 64 mode, you get double VGPRs. I think this is the thing I was remembering now. Right, so you got 1024 VGPRs across the whole SIMD unit. So why is it 1024 when you got a limit of 256? The registers typically hold. Right, so maybe it's because of the 64-bit data, I'm not sure. Because then if you double it, if you double the VGP, if you half it's 256. Oh, wait a minute. No, sorry. 1024 divided by 64, that's 16. Yeah, so if you don't want to get any. Is this right? You only want 16, really? That can't be right. Yeah, so it must mean that. But I guess if you run in like wave 64 mode. SIMD contains a total of 1024 VGPRs. So you get 16 VGPRs per. I'm not sure if that's right. Let's keep reading. The computational power of the dual compute units resides in SIMDs, which has been comprehensively enhanced for greater performance. Each SIMD can issue one wavefront, so 64 threads per clock to the AOEs, but longer latency. Kind of about execution. Right, I think this is just more about the we don't really care about this stuff so much. So where's the 256 number come in? Right, that's the question. Each short computer unit comprises 4 SIMD. What is this in? That's GCN, right? No? Each dual compute unit has 4 SIMDs that can execute a wave 32 for a total of 256 single precision floating point operations per cycle. Quite a lot. This looks interesting. How did that poll go in the end? I didn't even see the results. Oh, it is. Funny. Wait, did I even run the poll? I don't know anymore. Screw it, it's dark mode it is. So this is GCN, surely. No. RDNA, that sounds like. The result was no dark mode, was it? Ah, they didn't like the dark mode on the PDF. They're not be trolling me. I don't know why people like this. Is it just like reading text is easier in light mode, is it? Right, so the register file. Right, this maybe makes more sense to read. What does it? So you've got a register file of RDNA compute unit front end and SIMD. Right, yeah, the reason why I went to the wiki was so I can read from 2 to 3, but they didn't seem to from 1 to 2. But they didn't seem to sort of like tell us about the register file in there anyway. The fetch instruct each SIMD has a separate instruction pointer. Yep. 20th century wave controller, up to 80 wavefronts per compute unit. What is this? This information sounds wrong. Up to 80 wavefronts per dual compute unit. Wait. What am I reading? Right, so maybe there's even... Wait, maybe I didn't know this then. What? Right, so the more powerful compute units start with a dedicated front end, as illustrated in Figure 6. It could be that limits that are set by heuristics since you want to minimize register usage. At least on NVIDIA, less register usage equals more residual thread blocks on your MPs. I'm not sure what MPs mean. Yeah, so this, I don't know, this could be what I'm missing. I'm not sure. Multiprocessors, right? What's a multiprocessor in RD or in AMD speak? Is that the compute unit? I think it's okay. Like it could be limits usage and thread blocks, right? Okay, so the more powerful dual compute unit starts dedicated. Okay, blah blah blah. The L0 instruction cache is shared between 4 SIMDs within a dual compute unit. Yeah, so if I remember in the diagram, actually, 4 SIMDs just makes sense, right? You see here, they've got 4 of these blocks here. So these are probably the 4 SIMDs of 16, which, so yeah. I don't know why they got them in 16s though. So if there's 16, yeah. Wait. Yeah, 64 times 8, that's what I meant. 5. Yes, they're like 512. They're like AVX 512, but they've got 4 of them. So they got, yeah. So they've essentially got like a type of like a SIMD 2048 bit, which is 256 floats, as they said earlier, right? Cool. Right, so we're understanding that. So the L1 instruction cache is shared between 4 SIMD units within the dual compute unit, right? So if you have different shaders running on it, it shares the same instruction cache. Whereas prior instruction caches, right, we don't care about that. The instruction cache is 32 KB, set to four-way set associative. It is organized into 4 banks of 128 cache lines that are 64 bytes long. So the magic 64 number is still around, which is great. Good number. Each of the 4 SIMD can request instructions every cycle, and the instruction cache can deliver 32 bytes, typically 2 to 4 instructions every clock to each of the SIMDs, roughly 4 times bandwidth then. Okay. Interesting. Instructions fetched are disposed into 4 wavefront. Into wavefront controllers. So wavefront controller is here, I guess. Each SIMD has a separate instruction pointer and 20 entry wavefront controller. Right, so each SIMD of 16 has its own instruction pointer. But I thought you can only, there's only wave 32 and wave 64, so why is it at 16 then? But I guess it's just the way it is. For a total of 680 wavefronts per dual compute unit. That's what I don't get. Wavefronts can be a different workgroup or kernel. Right, I did not know this. So per dual compute unit, you can run 80 different right, so that's where the register allocation comes in. Okay. So although the dual compute unit maintains 32 workgroups simultaneously, the new wavefront controllers can operate wave 32 or wave 64. While the RDNA architecture is optimized for wave 32, the existing wave 64 mode can be more efficient for some applications. 10 wave 64 instructions. The controller issues and executes 2 wave 32 instructions. Yeah. Right. So I think I'm understanding this right. So a dual compute unit so a SIMD, one of the 4 SIMDs in there has a separate instruction pointer. And a 20 entry wavefront controller. Why 20 though? And a wavefront means like wavefronts can be from a different work group or kernel. So really you can have 20. That's the bit I'm not understanding. Because that means surely you can share the compute unit. I didn't think that was possible. Shader program instruction 1, 2, 3. I'm not sure. I'm not sure about this stuff. Oh, SIMD execution units can issue 4 instructions every cycle to SIMD. Oh, and this is the thing we read earlier. And then that was the thing we said the ALUs. All right. So this sort of like 20 entry wavefront controller. What is that? Any color-coded pictures? Yeah, they did have this one. So this is the RDNA, right? So you've got 32 on the left, 32 on the right. I forgot what these... Are these the wave controllers? I don't know if these really help. Help us really. So what is a wave controller? Because that's just really changing my understanding of how this all works. Maybe like a warp scheduler. Yeah. No idea. What about the... There's memory controllers in here. This is the instruction set architecture. Bernie Montana, my friend, thank you so much. Appreciate it. How you been? I've been good, thank you. It's going alright. We're just, you know, we found out some really interesting stuff today, I'll tell you that. We've been, well, we got anti-aliasing working. We started doing some clipping today. And then we got a bit sidetracked looking about, because I'm doing tons of switch statements. And I'm wondering how many sort of registers being allocated on the GPU. So we found out there's an environment variable you can set and it dumps some information, which is super handy. And we've seen the amount of like registers it allocates for our shader and that. And now we're trying to read into the RDNA spec to sort of figure out what this number means and how much I should keep an eye on it. But yeah, we've been working on clipping support today. So here's all some SDFs, got some SDF based clipping. We're trying to figure out like, we're trying to, we're trying to figure out if I can introduce many more switch case statements and if it doesn't mess up the amount of registers that get allocated, basically, and completely screw with the performance. So that's what we're trying to calculate right now. But yeah, we're doing all compute. Yeah, just compute. Do some SDF rendering for some UI. We're most of the way there. Just got to do clipping and transforms, rotating, that sort of stuff. I.e., decide to select instruction from the same warp if ready, or select other warp instruction. Right. Okay. So it's specific. So it's like a way of like switching between things. It's crazy. Yeah, definitely. It's not. Oh yeah, we need to do some optimization as well. That's the other one. We want to bin the draw commands per tile and do like a tile-based renderer for it, which shouldn't be too bad, too difficult to do. This is just describing the latency hiding though. I have no idea what AMD is smoking. Right. So fetch instructions are deposited into the wave controllers. This guy. This is a compute unit front end, right? It should have two SIMD units. Yeah, ALU 32, that makes sense. A register file of 100 and... What? But didn't they just say 1024? Didn't they just say 1024 in the other thing? They said 1024, didn't they? Times 4 for 32-bit, right? Times... What else are we times in by? They said they had like 1024 per compute unit, or dual compute unit, right? How's that 128k? What is... Well, maybe that's VGPR, but then there's a vector register file for something else. Because down here, they say they've got a SIMD. Oh, a SIMD contains. Yeah, but then this no, SIMD 0. Oh, I got confused. This is a dual compute unit. I thought this was the dual compute unit. This is the whole thing is a dual compute unit, which means because they said SIMD 16, right? This is 16 lower, yeah? 4, yeah, 8, yeah, 16. So it's 32 on the left, 32 on the right on this SIMD, right? Okay, so we've got a total of 1024 VGPR per SIMD. Right, this is making more sense now. So, which means that a total in a dual compute unit, or just in just a compute unit rather, you've got obviously 2048 VGPR. Wait, why do we want this number times 4, I guess? Why do I want to do that? That's not the register file. Right. That's 28. That's 128k like it said above. Oh, yeah. 32 lanes, that 32 bits wide. Right. 32 lanes. So per thread. 32 bits wide. Each vector driven plus register contains 32 lanes. Yeah, that makes sense. Right. And a SIMD contains 1024 VGPRs. So you do 1024 times 32, right? And that's a SIMD. But how do we get to 128k that we saw above? So you just hard code an entire game without building any interfaces? No, not at all. We're writing the render code. So we're just trying to render, like, get all the features in that we want. And then so I'm just figuring out to see, are all these features that we're adding in gonna give us a performance hit when I put them in? So we're just trying to work out hardware wise how it fits into like sort of average GPU on the desktop. I've got like a mid-tier GPU. Right, so we just did 1024 per SIMD. Per SIMD times 32 lanes, right? Because there's 32 lanes there. So we're trying to figure out how big this register file is. So this SIMD will execute the stuff in these, I think. Wait. I wonder where that 256 number comes from in the like, because the registers that can be is 256. If you read the assembly, or the maximum number v0 dash. Is that the maximum number? See, I'm not sure about that. So we've just done like 1024 times 32 basically, right? So we just got that. So we're times 4 off. Oh, I think you said times 4 size of float. Yeah, that's it, isn't it? Obviously. Thank you very much, Tanner. Appreciate it. And that was a long time that was dangling there. Right. Oh, so if we're looking at that then, that's your 128. Oh, that's bits to byte. I was gonna, yeah. No, that's byte, isn't it? It's K. No, it's K capital B though. Right. Yeah. Ugh. So where's the 4 times that we're missing then? To get that this is per compute unit. And SIMD. So am I confusing the fact that this register file here is 128. All of this. No. $1024 VGPL. Wavefront controller. Wavefront controller. And was it mentioned in text 4 cache lines of 32 KB? Oh. No, the cache. That's the instruction cache, maybe. Yeah, I think that's the instruction cache. So also looking at this sort of like wave controller. Optimizing for RDNA 2. This should be probably what we should have searched for. Syntax looks better. Whichever one is the C style. Architecture. Optimizations. Compute unit. Which one is this though? So this is GCN. Yeah, so GCN used to have 4 of those plus VGPRs. So it's got 4 SIMDs. Right, this feels much better. It's got some diagrams. With 64K VGPRs. So yeah, maybe that number was right actually. Yeah, it was bytes, wasn't it? Yeah, it was bytes, Glorious. So I just thought about that. I'm getting so tired, man. I'm getting so tired right now. Yeah, it was bytes, wasn't it? Then I read a comment. Okay. Yeah, plus that was right, wasn't it? It says 1024 VGPRs. Where's the number? We had the number. I went to college, but then I just dropped out because there's a load of crap in my local area, basically. I tried to go to uni after that. I tried to go to uni first, and then they said they would make me want to resit a year because I didn't know Oracle database, but I'd used MySQL. I don't know. The guy was just a complete twat. He just wanted me to sit my year again so they could bring in more money or whatever. I don't know. I went in there and just like spoke all the lingo, and the guy just didn't care. So I decided just to drop out and not bother doing it because it's just a load of crap anyway. And then I already had a job. It wasn't quite in the games industry though, which I wanted to. It wasn't in the games industry at all. It was just enterprise software, C# stuff I had at the time. But yeah, I just went and did that instead. In the very last Vulkan talks, there was a talk about doing graphics using computer. It was interesting. Sweet. Ah, was that the Vulkan conference stuff? That's starting to become my sentiment in general. Hmm. Yeah. Yeah, I'm not sure how good education really. Like my opinion of education is that it's pretty bad. It's, you know, but yeah, it could be done like way better. So got 128k. How we got that number? There's a SIMD unit, right? It's got 1020 volt VGPRs, 32 lanes, right? Times by 4 floats, right? So there's 1024 VGPRs. That's a lot. That's pretty good. Right. So we know that if we're allocating only... See, I don't know if this is right. It doesn't feel right to me. Huh? Oh, where did my thing go? Where's Miss Shaders? Do I have to do it like that? Well, I lost my shader information. Yeah, it's not the beginning. I'll just scroll up in the terminal. It's now disappeared. Maybe because it's not recompiled them. I have no idea. Oh. Computers, man. Computers. Right, so we've got that number. So the question is, if the SIMD unit can contain 10, 20 different instruction pointers, whatever it said. Right. What was that about? The fetch instructions are deposited into wave controllers. Each SIMD so this is a wave controller independent, or is it? Has an instruction pointer for 20 entry wavefront control and a 20 entry wavefront controller. Each SIMD has an... Oh, okay. Right. I get it now. So this is not me thinking... Right. So what I knew was right all along. Each SIMD has a separate instruction pointer. So it does run wave 32. Right. Each CU. And a 20 entry wavefront controller for a total of 80 wavefronts per dual compute unit. So why... That doesn't make any sense to me. Still. So there's that diagram though. We'll go to that other presentation in a second, but I think these are those wave controllers, right? No? No, because there's too many. Thank you very much, Anna. Appreciate it. Awesome. I'll see you in a future one. Yeah, it's strange, isn't it? I might have to clear the cache or something. There might be a new way, another way of getting it back. But yeah, we'll see. Anyway, I got this academia is full of dogmatic BS and has nothing to do with actual science. Just a bunch of dogmas. Yeah, pure insane. It's really bad, and it's like the best we can do apparently. And the worst thing is as well is people come out of there and they go into a job and they don't just the whole industry just gets messed up by it, like real bad. Like just look at like where most people will spend their time doing like making applications. It's just it's just insane. So GCN based GPUs have several compute units. The CU has, so this is GCN, right? Pretty cool. So this one is still GCN. GCN. Don't really care about GCN really. Oh. 4 CUs share one instruction and constant cache. This is where the shaders get executed. This is still GCN, isn't it? Each SIMD executes wavefronts of 64 size. Yes, GCN. In lockstep. 4 cycle instructions. 4 times SIMD 16. Ta-da! Maths. CU to work group processors. So this is the new terminology from RDNA. Oh, so RDNA has SIMD32, right? So it says I don't know. It's been confusing. I can say that. So you got the VGPR of 128 KB, which we saw, right? Which is 1024 times 32 lanes, right? Times 4 bytes per float, right? Or integer, whatever it's used for. Okay. So now we've got to figure out like how good of a VGPR, because we had like 34 VGPRs and that got, and it allocates it in 8 chunks, which will give you like 40, which gave us 40 VGPRs that were allocated on our shader. So we're going to see, is that a good number? This forces stats. Legendary. Thank you, Akraz. Appreciate it, my friend. I'm going to type this in. Mesa, shader, cache, disable. This is... that's good. Right. So we saw we had like 40 VGPRs allocated. So what does that number mean? And is it a good number? That's the question. JavaScript soy devs. Yes, I didn't want to say that, but yes. So an RDNA-based GPU has several worker processors. That's 2. Right, where is it? Yeah, that's 2 SIMD 32s. So 2 compute units. Wait, no, it's 4? Wait, I didn't know my RDNAs. No way. Oh, this is work group. Wait a minute. Let me find the diagram that I saw before. It's a dual compute unit. No, okay, this is surely this is GCN still. Seriously, is this all GCN? Yes, they're going to talk about GCN to RDNA. Right, okay. Why do they have to compare things? No, surely it's not. So dual compute unit. Maybe I'm a bit confused. Have a look. So RDNA based GPUs has several workgroup processors. Okay, well there's the answer. 4 SIMD32s plus the VGPRs. Okay, there's 4 of them. 4 scalar ALUs, right? Not really cared about the scalar stuff, to be honest. All seems pretty fine. 2 L0 caches, fair play. 1 instruction and constant cache. So 5 workgroup processors share an L1. Fair play. Good to know. And then 1 CU is about 1/2 of workgroup processor, or in other words, shoot, what am I looking at? What am I looking at? Or in other words, go to the next slide. 2 CU is about 1 workgroup. Okay. We'll go back to the diagram in a sec, just read the text. 1 workgroup has double the amount of SALUs. Right, scalar. Instruction cache and constant cache, I guess that means. There's a present mode. Man, Akraz, you got all the tips. It's amazing. You're a legend. Right. So 2 ALU. Why do they see 3 compute units in there? This is just a weird diagram. I guess what they mean is this is 4 of them. Right, so 1, 2. Right, so this is at the top. This one is GCN. Right? Whereas this is RDNA at the bottom. Okay, damn confusing. Imagine going over seeing the slides live and listening to this talk. Oh, I just have to come back for these slides. Right, so what they're saying is they've doubled they've doubled things. Hey there, Ram KXC. We're doing some research into RDNA 2 just to see if the stats. It's a bit of a complex one, but basically we've got some massive R switch statement. We've got this. Let's just run this right here. Right. We got this like super lovely compute shader which runs all these different SDF operations. It's pretty insane, and it's gonna be super awesome when it's finished. But the problem is I'm introducing. I've got about like 12 switch statements, and I want to maybe make it probably around 30 to maybe 50 switch statements, right? Case statements in switch statement. And when you branch in a GPU, you basically you typically need to allocate more VGPRs, which is like a vector register. And we got the stats back on the number of vectors. So before I go and do all the work and add tons of switch case statements, I wanted to see how many registers we were actually allocating. The number is 40 right now. And I want to see if that 40 number is a good number. So we're reading up on how GPUs work basically. And seeing on my card where the bottlenecks will happen based on the number of VGPRs we allocate. And from what I understand right now, well, no, I'm not sure if I understand it fully enough to make the judgment, but we're close. Each SIMD32 executes wavefronts of 32 natively, single instruction cycle. So there's one SIMD unit on the VGPRs that they're running, right? GCN to RDNA 2. Yeah, we don't really care about that. This is more high level. We don't care about the high level. Wait. Yeah, that's a specific card. Like my card, I forgot how many it had, but they have each card has a different number of uh, work group processors or compute units. Um, yep, we don't care about that one. There's no equivalent to L1 on GC. Right, new level of cache. Good, good, good. Anything else? Yep, yep. Went over this before. Single instruction, we knew that. Optimizations, right. Texture access workload. No. We can skip this one because I don't care about those textures. Could you do some prefix sum into more separate execution instead of switch? Into more separate execution instead of switch. Yeah, see the problem with that is we have to use the wave intrinsics and we have to be sure that we're running in wave 32 or 64 and know what we're doing, maybe. I'm not sure what you mean by prefix sum though and how that would work. So you're saying each thread will give me its... Because you need per pixel information. And yeah. As many caches, cache misses as possible. Yeah, we get that. Yeah, you kind of want to, you don't want to go across like that, you want to go across in this sort of order. Yeah. Cool. Yeah, because they cache in quads, basically. Which is pretty sweet. Means it's like two-dimensional, and there's even three-dimensional ones as well. So, but on some architectures they don't do 3D. I think that's mobile. On RDNA, the shader can run in wave 3264, not control. Not control within the shader, the driver chooses the mode. But if you look in Vulkan, there's a way to choose it or to suggest it. But how do you design for shaders? Wave multiples of 32. Well, yeah, that's why we did 8 by 8. But then you can't use the wave intrinsics then, so you have to really do two separate shaders. Assign threads within a work group. Well, where's the register allocation stuff we're talking about? Yes, this talks about if you use wave 64 and you take a branch, it could be an absolute bugger. Because you won't execute on all of your waves. On all of your threads, rather. All of your lanes, yeah. If you take a branch 50%, for instance. Whereas if you was running in wave 32 mode and had different things running, you only miss it, you know. You might get more utilization out of your threads, basically, because they're running two completely separate shaders. Yeah, LDS fast and global memory. Get to the VGPRs already. LDS. Did we just talk about texture access? Come on. No. This is a big talk. They must have sped through this thing. This is good information, not gonna lie. Oh, no, just gets Q&A. So from what I understand then, we've got 1024. Right. Let's go with what we know. Maybe we can understand exactly. This is 1024 per SIMD 32 times 32 lanes, right? So each thread can have a VGPR, and then you say times 4 for basically floats. So that's 128k of VGPR. So we're only doing 40. Like it's not using a lot of them, right? But then I'm curious why there's only 2.5. Like when you see the VGPR addressable thing here, how many of these can you access? Do 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 do. Can wrap around the pool. Fair play. Yeah, so I'm a bit. Yeah, maybe we just need to look at some more performance things, really. Shared intrinsics can reduce VGPR, register pressure, can be scalarized. Yep. We're trying to figure out like what is a good number, basically. Because I think when you go over 256, it sort of starts spilling. But if you've got 1024 of them, why is that? Or is it? No. I think there is 1024 because GCN has 256 of them. So maybe that's where I'm getting my information from. GCN has because it says 4 times the amount. Yeah, 4 times the number of registers as in GCN. Right, so this is where I'm getting my numbers from. So from what I remembered, there's when you go over 256 VGPRs, it starts spilling. But that's obviously that's GCN, right? Because there's only 256 VGPRs. But in RDNA 2, there's 1024, so there's absolutely tons of them. Fair play. Right, I have an understanding now. So it is about the spilling thing. That's right. So I got it all figured out. So this number, drop in the water. So we can add all that we want, and the register allocation shouldn't be that bad on the hardware that we're programming for. That is. So obviously, like if it was target older hardware or maybe some other hardware, yeah, it might have to be careful about it, but I think it should be fine, especially like on the high-end NVIDIAs, or mid-range NVIDIA cards. It should be fine. Oh my days. So the card that I have is the AMD 6600. So just to give you an idea of what this thing is capable of, it's 28 compute units. Is that the work? Yeah, so that means there's means there's 14 workgroup processors in it. And is that right? Yeah, I think that's right. I think that means the 32 lane thing. Something like that. Fair play. Right, so I think we've got a good idea now. This is good. So we're fine for adding tons more switch statements. That's the basic idea. So I'm happy about that. Look, all these damn branches. We might have to make sure that it does the branches right as well. It should be fine. That is legendary. So, yeah. So this stream we did get the clipping figured out at least. So we need to extend this clipping and make it super flexible, like all of this stuff is. We've got these different shapes we want to be able to do, and different operations like joining different clipping shapes together and making something really crazy, right? So, and maybe do subtraction. So in the next stream, we'll be finishing off the clipping stuff and making even more crazy switch statement stuff, and it should just be fine, basically. Fingers crossed. Right, I've got a jam because I got work tomorrow. But yeah, I'll next be on Sunday, 4 p.m. GMT +1. And I'm glad we figured all that out, but that was just so tiring. Oh my days, what is all of this stuff? Come on. Pure insane. Like, you come on here, I don't even... All I go on is that, you know, science and... Sorry. Software and game development. You just get all the absolute trash at the front. Pure trash. Oh, my brain is tired. My brain needs to go to bed. Thanks for all the help, guys, and all coming and chilling. It's been pretty good, and learned a lot today. And reaffirms what I know as well, which has been good. Let's raid this Jai guy. Alright, I'll see you all on Sunday, or Tuesday, or Thursday. Check the About section for links and stuff. And yeah, for those who have access to the code and everything, I'll see if I can get that up tonight. And I'll drop the VOD on YouTube, obviously. But yeah. Have a good start to your weekend, everyone. And I'll see you all in the future one. Right, good night.